Let us now talk about analysing simple harmonic motion. If we were to examine the kinematic properties of something undergoing simple harmonic motion, like a mass spring system or a pendulum swinging backwards and forth, well, the very first thing we need to do is to measure certain things about it. Now, a very important part of this is where do we place a fiduciary marker, a fiducial marker. Now, fiducial marker is something that basically you time from when the mass passes that point. So basically just a bit of blue tack or something would do it. Now with both, we do it at the point where the velocity is highest. So in the spring mass system, it's where the mass is when it is at rest. And in the pendulum, basically directly underneath, so where a plumb bob would lie. And the reason for this is you need it to be going very quickly past that point to reduce the measurement uncertainties. If it's going to slowly past that point, then you don't really know when it is exactly at that point. Making it, placing the fiducial marker at exactly the point where it's going the fastest, that is the best way forward. So as we were to watch the object move backwards and forward past that point, it would trace a displacement as it goes through its cycle. Now imagining that it has a cycle, and that is 2 pi, you can see this graph at the top here, this blue line. This represents our object going to one extreme, passing through the midpoint to the other extreme, passing back through the midpoint back to where we began. And the dotted line, the first dotted line, that 2 pi represents a whole cycle that has occurred. If we look at the velocity, we notice something very interesting indeed. The velocity is shifted slightly. So look where the peak lies with the dotted line on at 2 pi, and notice that the velocity's peak is actually at pi over 2, or 1/4 of a cycle before that. It's actually arrived first. And so what this means is we had the maximum of velocity when the pendulum was moving through the midpoint, or the mass of the spring mass system was passing through its undisturbed position, which is of course 1/4 of a cycle before it reached its extreme end. The whole graph is shifted by 1/4 of a cycle. Is there a mathematical reason why it should be so? Indeed there is. But before we get to that, take a look at what's happening with the acceleration. For you see, the peak of that graph is shifted by 1/4 of a cycle. Still, it is 1/4 of a cycle in front of the velocity, meaning it's a whole half a cycle, pi radians different to the displacement. It means that when our pendulum is at its far right, at its most positive in its position, its acceleration is greatest to the left, greatest in the negative. And that is exactly what we expect to see with simple harmonic motion, because what we say is that there is a restorative force acting back towards the midpoint that is in proportion to the displacement. It is greatest and most negative when the displacement is greatest and most positive. So if we were to look at that motion, we could draw it. Imagine that our pendulum was swinging backwards and forwards, and it was dripping paint as we pulled a sheet underneath it, or a conveyor belt. We would see it draw out this trigonometric function, a cos graph. Now this is a straightforward cos graph, y equals cos theta. And I prefer to use a cos theta graph here simply because a cos theta graph starts at 1. Now, if we've got a pendulum, we would normally start it extended at its at its furthest displacement. So if it was a pendulum that was going to be displaced with an amplitude of 1, we would start this at 1. It couldn't be a sine graph unless we started our timer at the point where it goes through that fiducial marker, which we could well do. Either way, let's have a little look at what happens. So this cos function here, it's unspecific to any examples we might use. It is just a generic cos graph. We need to scale it in terms of its height and also its temporal properties. At the moment, what we have here is a graph that completes one whole cycle after 2 pi. Now, what we need instead is we need to scale this in terms of it's going to complete one complete cycle after a period of time. We want this a displacement time graph. And so what we're going to have to do is our cos term is going to be cos of time. Now, if we had something that went through 2 pi in 1 second, then we'd just do 2 pi t, cos of 2 pi t. But if it did its whole revolution twice a second, then it would be 4 pi t, or 2 pi 2t. So what we put inside that bracket next to the t scales horizontally on a displacement time graph, our graph, so that it matches our oscillation. We must put 2 pi multiplied by the frequency, which is the number of times per second this oscillation happens, multiplied by the time. And then for any time, we could find out its position in this cycle. But of course, this is assuming that our oscillation has an amplitude of 1 meter, which it may not. So what we would have to do is scale this 1 meter amplitude by whatever the amplitude of the oscillation is. If the oscillation is greater than 1, we must scale it by whatever factor this amplitude is greater than 1. So for example, if the amplitude was 2, we'd put 2 cos 2 pi ft. So here we have x equals a, the amplitude, multiplied by cos 2 pi, the frequency, times by the time. And at any particular time, knowing just the frequency and the amplitude, I could work out what its displacement was at that time. It just follows this simple cos graph. And now I know that the gradient of a displacement time graph or a distance time graph would give me the velocity. I also know that Isaac Newton and Leibniz invented this thing called calculus, which enabled me to work out when I have a function what its change with respect to time would be. So if I wanted to know how x changed with respect to time, or indeed the gradient of this graph, I would have to differentiate with respect to time a cos 2 pi ft. Now cos terms go to minus sine terms, and anything inside the bracket there, 2 pi f, multiplies by the whole thing. A is not dependent on t, so it stays there as a constant, and I get minus a multiplied by 2 pi f, which has come out of the brackets there, multiplied by sine 2 pi ft. Now, what's going to happen? The maximum velocity is going to occur when the multiplier on the right, the sine 2 pi ft, is equal to 1. It means that my maximum velocity occurs when I have 2 pi f a, basically. And I'm slightly obscured there in this video, but the Vmax would occur at plus or minus 2 pi f could be represented by omega, the angular frequency, multiplied by the amplitude. Now there is a more general term that the velocity at any point can be given by plus or minus w omega square root of a squared minus x squared. Let's have a look at where that comes from. So strap in, this is quite long, and you don't need to know how to do this for the exam, but if you want to know where it comes from and to prove to yourself that the velocity at any particular point, any particular position in the cycle. Now, everything we've done so far, we've been talking about its position with respect to time, even its velocity with respect to time. What is different about this is its position with respect to its velocity. What is its velocity when it is at a certain position x? And what we're going to derive is that we can find that velocity, and it's plus or minus because it could be going through that point in either direction. The angular frequency omega multiplied by the square root of the amplitude squared minus its position squared. So I want to know what is its velocity at that position. So the very first thing we need to remember is that we could write sine theta squared as sine squared theta. So this is just a mathematical shorthand. So when you see this later, you'll realize that this is something we have used. And there's this trig identity, the most famous of all, that sine squared theta plus cos squared theta equals 1. You're going to need to remember that for this derivation, which means we can write it out like this, that cos squared theta is equal to 1 minus sine squared theta, which I've represented here, sine theta squared. Now don't worry, I've used both ways of writing it in this, and that is I want something to stay clear for later on. So therefore, if I've got cos squared theta, which is the same as cos theta squared, if I square root both sides, I get cos theta by itself. And that means, of course, I square root 1 minus sine theta squared. Now, since we can write that the angular frequency is the angle turned through per unit time, we can get an expression for the angle we've turned through by multiplying the angular frequency by the time. That's going to be useful because we can substitute it there on that left-hand side and on the right where the theta existed. So we've now got cos omega t is equal to the square root of 1 minus sine omega t squared. Now we're going to set the expression for the displacement. This is the thing that's slightly interesting. If we decided that we were going to start our displacement term with the pendulum extended to its amplitude, basically from the pendulum, we're going to start the timer when the pendulum is at its extreme to one left-hand side. It would be x equals a cos omega t, but because we're going to start the timer when it goes through the fiducial marker in the middle, even though that's not where it started, that's where we're starting time, it's better to represent it as x equals a sine omega t. And it becomes very convenient in this derivation to call it that. Now nothing has changed, it's just the point at which we're measuring the time from. So we're going to use this latter term, a sine omega t. Now, what we understand, if that is a representation of its position with respect to time, the velocity would be differentiating this term with respect to time, a sine omega t d by dt. And so that pulls straight out, the sine term goes to a cos term, the omega inside the brackets comes out to multiply by the non-time dependent a, so it becomes a omega multiplied by cos omega t. And then, because we've got over on the left-hand side, if you remember, we got an expression for cos omega t in terms of sine, we can substitute in the square root of 1 minus sine omega t all squared into that expression there. And then the very first thing we want to do is, if we look and we represent the a, and this is a bit of a stretch, a is equal to a squared square rooted, that equals a. And we're going to put that just there, just so that we can see how that then we can simplify the surd there. We can move it into the square root. And so by multiplying omega by the square root of a squared, and then multiplying that by the square root of a whole bunch of other stuff, well, what we can do is we can bring it inside that square root. And so we just extend the square root over the end, and we end up with the velocity is equal to the angular frequency multiplied by a squared multiplied by 1 minus sine omega t all squared. Now, if we multiply out that, so we've got a squared multiplied by 1, and then we've got a squared multiplied by sine omega t squared, we end up with an expression v is equal to omega square root of a squared minus a squared sine omega t all squared, which we can bring that a squared that is next to the sine omega t inside the square, and the bracket just there. And what we basically have is we've now got an expression a sine omega t squared is an expression for the position, if you remember. So look bottom left, a sine omega t is equal to the position. So therefore that bit on the right hand side, a sine omega t all squared, is the same as the position squared. And so it's obscured in this video by my head. You can see that v is therefore equal to, and it would be plus or minus because it can go through either way, omega, the angular frequency, multiplied by the square root of the amplitude squared minus the position squared. Isn't that nice? I think so. And that's not where it ends. Of course, we could differentiate again with respect to time, that expression that we just got. And of course, what would happen is the sine would go to cos. The minus a 2 pi f would stay the same, but what's inside the brackets, so the 2 pi f would come out and be a multiplying factor once more. So we'd have minus a 2 pi f from before, multiplied by a new 2 pi f from the brackets, multiplied by cos of 2 pi ft. And so we'd end up with an expression for the acceleration, which would be minus a 2 pi f all squared times cos 2 pi ft. In other words, this expression here, which is more general, we could figure out then that the maximum acceleration would occur when the multiplier on the right hand side, the cos 2 pi ft term, was equal to 1, and so far. And so the maximum acceleration would occur when we had 2 pi f squared times a, or alternatively written, the maximum acceleration would occur when we've got omega squared multiplied by the amplitude. Have we seen this before? Yes, indeed we have, and we saw it in circular motion. If you remember that force equal to m omega squared r, if you imagine that the radius of the circle is just the amplitude of this pendulum swinging, then the r becomes an a. If you imagine that force is equal to mass times acceleration, then acceleration is equal to F divided by m. So if I had m omega squared r and divided it by m, then we've just got omega squared r. And if the radius was equal to the amplitude, we've got omega squared a. The acceleration is equal to omega squared times the amplitude. It is the same as the formula for centripetal force in terms of the angular movement around in a circle. And it's quite clear to see that sine and cosine are a quarter of a cycle apart from each other. It means because we go from, in this derivation, we did position as a cos term, and we did velocity as a sine term, and there's acceleration as a cos term once more, this is where that quarter of a cycle comes from mathematically. And if we were to draw these three quantities, we would see that they were always out of step by a quarter of a cycle. And it's also important to remember what is physically going on when the displacement is greatest to the right-hand side, the velocity is 0, but the acceleration is greatest to the left-hand side at that moment. And remembering the physical reason why these terms are out of phase. So there you can see they're all out of phase with each other. But here's an interesting thing. On the previous diagram, the velocity had a smaller amplitude than the displacement, and the acceleration had a smaller amplitude still. Here, it's the opposite way around. Velocity is greater amplitude than displacement, and acceleration greater amplitude still. So what is it that affects that? Well, it's the 2 pi f term. If the 2 pi f term is greater than 1, then when we differentiate it, we're going to multiply it by a number that's greater than 1, which is going to make the derivative bigger by this multiplication by a number larger than 1 than the original. And so this graph here, 2 pi f is greater than 1 in this graph, and in the graph before, 2 pi f was less than 1. We were multiplying our derivative by a number that was less than 1, so it was getting smaller as a consequence. Now we might be given a question that draws the displacement and asks us to draw the velocity with respect to that. One of the most easy things that they could do is give you a situation where 2 pi f was equal to 1, and so therefore the each of these would have the same amplitude as each other. You're just multiplying by 1 each time you differentiated it. So they should have the same amplitude in that case. But you've got to get it right. The velocity is shifted earlier. You know, the peak comes quarter of a cycle before in terms of time than the displacement. It shifts like towards the beginning of the time when the time was measured. So remember that that is the thing. You might be asked to draw basically a wave that is 1/4 of a cycle, pi over 2 different from the original. That's a very typical exam question for this. And remember that the thing you can always just pull it back to is what is the gradient doing at this point? If the gradient is 0 on the displacement graph, then we expect the velocity to be going through 0 at this point, which indeed it does if you just look at it.